Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Before you proceed, I'd like to request our members to kindly subscribe, engage us in the comment section, and also check our description boxes for various videos that we're going to do, which are basically similar to this. And of course, engage us in the comment section for more. So today we're going to look at the concept of the translation partition function. And of course, this is one of the aspects of the energies which we had described in our previous videos on the concept of various types of energies states for a molecule. Now, in this case, we had mentioned that the general description for the energies of a molecule can be given in terms of UV rotation plus UV translation plus UV. We had talked about electronic plus UV vibration as the various states of different energies of a molecule, or various states in which the energies of a molecule can be described. Now, in this case, for us to find the translational partition function, we're going to consider the energy of a monoatomic ideal gas. And basically, we're going to consider the concept of a monoatomic ideal gas, since this is the only aspect of energy which is going to be described for the motion of this specific particle, and therefore this is the element that we're going to consider from our previous discussion. And in this case, we're going to use the concept of quantum mechanics of an atom, and basically which is going to entail the concept that we have discussed in our previous videos on a particle in a box. Now, this is going to use the concept of a Schrodinger's equation, and of course from the concept of a Max-Born of course, interpretation of the concept of a wave function, which we have simply given in terms of u are given as such. So therefore, from the Max-Born interpretation of the concept of the physical implication of this specific wave function, we're going to use this one in collaboration with Erin Schrodinger's, of course, a description of this specific energy of a particle in a box. And those two ideas are going to assist us, of course, find a way of describing this translational partition function of a monoatomic gas. Now, from Born's description, he said that basically, if we consider a particle in a box by using this wave function, which is a probability of finding a particle, we're going to use the concept of a particle in a box by considering the dimensions of x equivalent to 0 to xl, and basically that one implies that the length of this particular box is going to be given as a width of L from x is equals to 0 to x is equals to L. And then we have these specific walls which are infinite walls, and the potential inside this specific box is going to be given as 0. Therefore, we're going to consider that for us to find a particle, the possibility of finding a particle as it approaches a wall is going to be given as almost 0. The wave function, then therefore approaching these two specific sets of box is going to be going towards the 0 potential. So therefore, we're going to consider the dimensions of this particular aspect of a particle in a box, and we're going to use a 3-dimension box in that specific case. Therefore, the representation of this particular energy according to Einstein, using this wave function from the box, we're going to have this representation of this energy given in terms of a 3-dimension aspect of x, y, and z, using this various range of quantum numbers which are going to be given in terms of the square. And then we're going to have this one multiplied with the square of a Planck's constant, and the denominator is going to be given in terms of 8, the square of pi, and then this is just 8 ml squared, where L is the dimension of this specific box, m is the mass of that specific particle, and then nx is the quantum number that is associated with this specific dimension of x, y, and z coordinates. We can consider this one as a Cartesian coordinate system if we are going to consider 3-dimension box given as such. So therefore, this one can be assumed to be a length, width, and height of this specific box that we're going to consider, and then a particle being located inside the air can be described using this specific description from Erin Schrodinger. So if we look at this particular concept in that perspective of a particle in a box, we're going to consider as a particle in a box, of course, a one-dimension particle with a potential that has a dimension over L given as such. And this, as I said, the wave function is going to be described in terms of a sine function given as a the sine over n pi x over L. And in this case, this aspect over n is going to be given in a one dimension, perhaps the nx given as such, and then we're going to have pi x over L given in that specific order. We're going to see that this aspect over n x pi over L is going to represent a constant, and basically this is a derivation from the wave particle in a single box, or the particle in a box given that. So we can find the potential of this specific particle within the box using the what we refer to as the Schrodinger's equation, and I'm just going to give a representation of that specific equation in a single dimension, just as I mentioned. So I'm going to do away with this. Basically, this is just a wave representation of that specific wave function in a box. So if we have that particle in a box with a potential 0, we can give this version of Schrodinger's equation, which is h squared over 8 pi m, and then we're going to have this one given in terms of so this is a portion of the differential operator, which is what I'm going to consider one dimension of the x-axis. As we have said, basically this is going to be a one-dimension box, and therefore we're going to consider this section of the operator, which is going to consist of just only the x-axis, and this is going to be a function of course, the wave function given in terms of u given as such. And of course, we said that the Schrodinger's equation is going to represent a equation that's going to provide a solution for various quantum numbers, and therefore the application of this is going to give us the particular probability of finding that particular particle in a box. Now, solving for this specific function for u, this is going to give us the internal energy given in terms of the square of m h over 8 ml, and then the square of that one. And of course, that is going to represent for us the various energies or the potentials which are going to be used in describing that various aspect of the box. Now, to be specific for our case, we're going to see that n is going to be given in terms of x, and that is basically going to solve for us the specific way of representing this specific particle in a box given as u. And this is going to assist us describe the various aspects of x, y, and z for a translational partition function of this specific particle that we refer to as a monoatomic ideal gas. So therefore, we're going to consider this specific case, whereby we can have a version of this partition function given in terms of the summation of the energies in this state of nx, or the quantum number nx, and then the summation of the quantum numbers y, and then lastly the summation of this quantum aspect of quantum numbers in the state of x. And we're going to have the exponent of this various range of quantum numbers for the. Now, we have mentioned the concept of this specific aspect of degeneracies. So we're going to have the quantum number for x being represented as nx, the square of that, and ny, the square of that, plus nz, the square of that. And then this is going to be basically a negative value because of that negative b that we have mentioned. And then we're going to have this one divided by 8 ml squared kb t given as such. So this is going to represent, so we have this specific element of h squared given at that specific point. So this is going to be a general representation for a partition function representing the translational partition function of that specific particle. And of course, we're going to use the laws of logarithms in order to try and give this version of the equation in a form that is more simplified. So I'd say that in case we have the exponents of specific functions given in terms of a product, then we're going to find the sum of those specific exponents. In case we're given in terms of perhaps a summation, then we're going to find the multiples of those specific components. Therefore, this specific equation can be solved in terms of finding the product of various aspects over n for the state over n, y, and z. And perhaps if this space is going to be enough, we can have the summation over energy of this specific component for the quantum number n given as such, and then we're going to have the exponent negative nx squared h squared, and then this is all over 8 ml squared kT. And this is going to be replicated for the values of quantum numbers for ny and z. Perhaps because of this, I'm going to limit this one to this, but this is going to be analogous representation for the second state of summation of ny, the exponent of negative mx squared. So it's going to be not x squared, but mxh squared all over 8 ml squared kT. And then this is going to form also the last bit for n z given in that specific order. So therefore, this is going to be considered for the translational partition function. But in case we had this specific box that we're going to consider in three-dimension space equivalent in terms of nx, ny, and z, we can have a general representation for the partition function of this particular particles given as the summation over nx, which is basically representing a similar set of equivalents for nx, ny, and z. And this is going to be given as an exponent of negative nx squared h squared over 8 ml squared kBt. And these are going to represent the various states of these three particular functions, and we're going to have a cube of this one. Now, having concluded that basically the concept of this equivalent to this one for these various states of quantum numbers. So this is going to give us a general representation for the translation partition function of a monoatomic gas, having considered the particle in a box and the Schrodinger's equation and the Max-Born approximation, and therefore this is going to be a final set of what we refer to as the translation partition function. I'd like us, of course, to be maybe taking hints on the various systems that we're going to take. Of course, they are going to be voluminous, but of course, they are going to assist us in coming up with various representations that we're going to look for in partition functions of various thermodynamic variables. So that is it for now, guys. Bye, God bless you. Catch us in our next video.